Greetings, everyone. My name is Hao Tan. I am a first-year doctoral student from the University of Waterloo. Today, I'm going to present our brief announcement, a closer look at quantum distributed consensus. Consensus protocols are crucial building blocks of today's Internet service infrastructures. As the scale of the service grows, data is replicated to ensure better availability and query response time. Consensus protocols guarantees the consistency of replicas by enforcing a strict ordering of concurrent operations. Consensus protocols solve the consensus problem by coordinating a set of processes holding different input values to reach an agreement on the output. Solution to the consensus problem must guarantee the following properties. The termination property ensures that each process eventually decides its output. Validity property ensures that decided value must be the input of some process. An agreement property ensures that no two processes decide conflicting values. Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computation. In 2008, HOLM proposed a protocol for solving distributed consensus using quantum technique. This protocol consists of three simple steps. In the first step, entangled qubits are distributed to all participants. In the second step, each participant will measure its qubit. And finally, the measurement will lead to the collapse of superposed quantum states. Since quantum entanglement will guarantee entangled qubits collapse to the same state, all participants reached agreement. HOLM asserts the protocol refutes the FLP impossibility result, which said that consensus is not achievable in an asynchronous environment despite of a single failure. However, the protocol guarantees only agreement property but not a validity property. It raises an interesting question. Do qubits and quantum entanglement offer any advantage at all over classical protocols for consensus in terms of correctness? To answer the question, we consider binary consensus problem where all inputs are joined from 0 and 1. To model the environment quantum consensus is targeted for, we assume no two processes can communicate by exchanging messages, except that some shared state can be distributed to both processes during initialization. For simplicity of analysis, we assume the inputs of all processes are chosen independently and uniformly at random after initialization. We modeled the absence of communication among processes by the following assumption. For any process Pj, for any output value Oj prime, and for any combination of input values I1 prime to In prime, the following holds. The probability of Oj equals to Oj prime under the condition that I1 equals to I1 prime to In equals to In prime is the same as the probability of Oj equals to Oj prime under the condition that Ij equals to Ij prime. This equation implies that for each process, the probability of deciding a specific value is completely determined by the protocol and the process own input value. Inputs of other processes have no impact on that probability. Here I present our main result. The probability distribution over outputs in any n-process classical or quantum protocol is constrained by the following upper bound, where PA represents the probability that outputs satisfy the agreement property, and PV represents the probability that outputs satisfy the validity property. This upper bound captures the inherent trade-off between the probability of achieving agreement and the probability of achieving validity in the absence of communication. The upper bound defined in the previous slide is matched by several classical n-process protocols. For instance, the protocol that all processes output a pre-shared arbitrary bit regardless of their inputs, or the protocol that all processes always output their input. or the protocol that all processes execute the first protocol with probability t and the second protocol with probability 1 minus t, where t is a pre-shared random value in the interval between 0 and 1. This slide presents the simulation results of the third protocol, which shows the probability of agreement and validity for various values of the parameter t. We plot 50 points for each value of t, and each point is the average of 1,000 rounds, with binary inputs generated independently and uniformly at random. The red line in each plot is the optimal upper bound defined earlier. We can observe that point cloud for each value of t is scattered symmetrically about the optimal bound, which further validates the bound. Also note that HOLM's protocol will generate similar point cloud as the case where t equals to 1. The results also demonstrate an interesting behavior of the agreement versus validity trade-off. As n increases, the optimal trade-off converges to a horizontal line, PV equals to 1. In other words, validity is almost guaranteed by random chance when many processes participate with inputs chosen independently at random. In conclusion, HOLM's protocol is not inherently more powerful than classical randomized protocols in this context. Our results prove that quantum entanglement is not helpful for solving distributed constances in the absence of communication. In other words, quantum entanglement is not a substitute for interprocess communication. Thank you for watching.